Prove using vectors the sum of the distances from a point O in space to the vertices of a triangle ABC is equal to the sum of the distances from that same point O to the midpoints of the sides of the triangle. Okay, now let's try to understand with the help of a diagram. We begin by considering a triangle with vertices given by A, B, and C. And then we have a point O in space. So let's assume that the O is the origin of some coordinate system. Then we can define the position vector of each of the three vertices A, B, and C with respect to the origin O. So here we'll assume that the position vector of the vertex A is defined by the vector A. Position vector of the vertex B, let us define it with the vector B, and C with the vector C. It simply means that we have a directed line segment joining the origin to each of the vertex. Fine. Now that we have the position vector defined for each of the three vertices, let's find out the midpoint of each of the three sides. We'll assume that the midpoint of the side BC of the triangle, that we're going to denote it by D. Then we have the midpoint of the side CA, we're going to denote it by E, and midpoint of the side AB, we're going to denote it by F. So we're also going to define the position vector of D, E, and F with respect to the origin O. So our goal will be to prove that if we take the sum of the position vectors OA, O plus OB plus OC, that means the sum of the position vectors of the vertices of the triangle, this must be equals to the sum of OD, OE, and OF. Okay, let's begin. So first we'll define the position vectors of A, B, and C. Now next we will define the position vector of the midpoint D of side BC. Here D is the dividing DC into ratio 1:1. So here internally, so here we can use the internal section formula. So we have OD vector. So using the section formula, we're going to get B vector added to C vector whole divided by 2. Fine. Similarly, we can define the position vector of the other two midpoints, so OE vector. So that's going to be A vector plus C vector divided by 2, and OF vector, so that's going to be equals to A vector plus B vector whole divided by 2. Fine. Now let's do one thing. So we'll start from the left hand side here. On the left hand side we have OA vector plus OB vector plus OC vector. Now OA vector is simply the position vector of the vertex A, so that's A vector. OB will be the position vector of vertex B, so that's B vector, and OC vector is the position vector of vertex C. So this is A vector plus B vector plus C vector. And if we go to the right hand side, so here we have OD vector. So here in place of OD vector, we have B vector plus C vector whole divided by 2. Then we have OE vector, so that's A vector plus C vector whole divided by 2. And then we have OF vector, so that's A vector plus B vector divided by 2. Now we're going to take the sum of these three vectors. So we're going to have a common denominator of 2. So in the numerator we have A vector and A vector repeating twice with 2A vector, plus B vector gets repeated twice, so that means we have the sum equals to 2B vector, and then C vector is added to itself 2 times, so we have 2C vector. We can factor out the 2 from the numerator and the denominator, leaving us with A plus B plus C vectors. Now clearly the left hand side equals to the right hand side, so we have successfully proved a problem which the original statement was the sum of the distances from a point O in space to the vertices of the triangle ABC. It's going to be equal to the sum of the distance from the same point O to the midpoint DEF of the sides of the triangle.